My name is Helen Sanders from Techniform. Thank you to my Australian friends. What I'm going to do today is talk about why U-factor is important in hot climates. And I have to say, for a number of years, I've been focused on the center of glass, and the penny dropped for me about a year or two ago as I moved to Techniform and started to look at the edge of fenestration, the frame and the edge of glass. And originally, I thought that U-factor didn't matter in the summer, and it didn't matter in Florida, and it didn't matter in Arizona, because it's all about the delta T, the difference in air temperature between inside and outside of the building, right? Now, in Minnesota or in Alaska, you've got a massive temperature difference between the inside of the building and the outside. Minus 40 degrees C in the winter, and 20 degrees C in the inside. So that's a massive delta T. And in Florida, maybe if you keep it 20 C inside, you've got maybe, 30, 40 outside? That's a very small delta T. But that's not the temperature difference that matters for fenestration. It's the temperature of the frame. Now, anybody who's been outside in the summer in a black t-shirt knows you get pretty hot pretty quickly because of solar absorption. The same thing happens in a window system, especially an aluminum or aluminium window system. Especially if it's dark, you get a lot of solar absorption, and suddenly the temperature of the frame is way hotter than the temperature of the glass. The temperature of the air. So you might have 30 degrees C air temperature, but you could get a very, very hot frame, 60, 70 degrees C very quickly. And so when you have that kind of temperature in the frame on the outside, where's that heat going to go? It's going to go straight to the inside if you don't have a thermal break on the frame, or you don't have a thermal break on the edge of the glass. So I could stop there because you kind of get that. You can see why the penny dropped for me, but a lot of you want to see data, so that's what I'm going to show today. So there's a study that was done in Singapore, hot, humid climate, by the Solar Energy Research Institute of Singapore. It was done for Techniform and supported by a number of companies and organizations whose names are listed up there. What they did was they took a series of different aluminum or aluminium, depending on where you live, framing systems from a non-thermally broken system that you can see on the left there, through from a low performance thermal break, medium performance thermal break, and then a very high performance thermal break on your right. And what they did is they installed it in a test building that you can see here. And they instrumented it. They put thermocouples on the inside, thermocouples on the outside. They used dark-colored frames. They used light-colored frames. And I'm going to show you some of the data. So this is the 50-day mean daily heat gain for those 4 different frame types. So you can see the no thermal break, dark color on the left. And then going to low, medium, and high. And you can see the reduction in that mean daily heat gain as you go to better and better thermally broken systems. Now, let's talk about temperature. So these behind me, you'll see the temperature of the frame for the light-colored systems from non-thermally broken through low, medium, or high thermally broken. Now, you might think this is the temperature of the outside of the frame, but it's not. It's the temperature of the inside of the frame, right next to where you might be sitting. So can you imagine sitting next to that frame? 48 degrees Celsius. That's pretty uncomfortable. And you can see, by the time you get to the high-performance thermally broken frame, you're down at 35 degrees C, which is close to body temperature, pretty comfortable. This is just an IR picture of the different framing systems from thermally broken on the left sort of very non-thermally broken on the right. Dark and light colors, just some examples of, to give you a sense of the temperature differences. Now, this is not just about energy. Obviously, energy is important, but it's also about comfort. If you're sitting next to those frames and it's 48 degrees Celsius, that's pretty uncomfortable. Now, there's been some studies to look at the impact of temperature on productivity. This graph, the line in green, shows you the relative productivity as a function of temperature. So studies have shown that if you're basically between about 71, 72 degrees Fahrenheit, around 21 degrees Celsius, that's optimum for productivity. Every degree Fahrenheit or degree C that you go outside of that range, either higher or lower, hotter or colder, you lose about 1% of productivity. So you can imagine you could be pretty unproductive sitting next to that kind of poorly performing window if you don't thermally break it. 12% productivity loss between 25 degrees C and 33 degrees C. So pretty impactful. So going to dig a little into some technical, and so I'm going to show an equation here. I know it's early in the morning and we had the dinner last night, but this is actually the relationship between solar heat gain coefficient of the frame and U factor. So U factor actually helps determine what the solar heat gain coefficient of the frame is, which is why U factor is really important. So it's solar heat gain coefficient of the frame is proportional to the solar absorption of the frame. So the darker the frame, the more absorbing. The U factor, and then it's also has a relationship with the frame surface heat transfer coefficient. And the ratio of the wetted surface area of the external frame and the projected surface area. So if I think about a mullion, the projected surface area is the bit that you see, the wetted area is the entire area that is exposed to the outside. So that's the equation if you want to calculate solar heat gain coefficient of a frame, should you care. And I did the maths for you here for to compare the solar heat gain coefficient of a non-thermally broken frame to one that's thermally broken one. So start with a frame area about 0.5 meter squared, glass area of 1.5, wetted area to projected area of 1.2, assuming a heat transfer coefficient of about 18 watts per meter squared Kelvin. And then if you plug all those numbers into that equation, what you get is solar heat gain coefficient of the frame of 0.23 for the non-thermally broken and 0.08 for the thermally broken. So really pretty different. Now, of course, that's the frame, so you have to calculate what the solar heat gain coefficient of the whole window is, and of course that's just a weighted average. And then if you do that, you end up with solar heat gain coefficient of the window 0.32 versus 0.28, which of course is going to change depending on what the size of the window is versus and the frame area to glass area. But just as an example here, you see there's a 13% reduction in overall solar heat gain coefficient of a window when you use a thermally broken frame. So here's some data when we look at the impact, the U factor impact on the energy performance of a building. So this is not real measurements. This is a thermal modeling. This was done in IES. So what you see here for this building that you see on your right, a prototypical building, we have the total cooling load on the left, the bars of the total cooling load, and then the envelope thermal transfer value, which is basically the amount of energy going through the envelope, is the green line. And it's for 5 different conditions. One is a typical base case in Singapore, which has a U factor of 2.8 watts per meter squared Kelvin. that building with non-thermally broken aluminum window frames with a U of 3, then a low thermally broken system, a medium thermally broken system, and then a high thermally broken system. And you can see that when you get to the thermally broken systems, you're improving the energy performance, and the highest thermally broken system improves it by 6.5%, which is not too shabby. And then you might say, well, improving the solar heat gain coefficient will do just as well. Be better, right? Be better to just improve the glass. But let's take a look and see what that does. So this is when you're holding the U factor constant at 3, and you're improving the solar heat gain coefficient of the window through, say, improving the glass. So solar heat gain coefficient going from 0.25, 0.223, 0.22, and 0.21. That improves it by 6%, which is basically what we did by improving the U factor, by improving the frame. So I hope that gives you some reason to put thermal breaks in your window rather than just focusing on the center of glass. It makes a big difference. And of course, if you stop the heat going through the frame, but you don't stop the heat going through the center of glass, you've still got a problem. Just like in cold climates. Start from the edge, improve the frame, then thermally break the edge of glass, put a warm edge spacer in there, and then look at the center of glass. So, talking about the edge of glass, just want to spend a few moments here to talk about a project that's near and dear to my heart in Seattle. Now, you don't imagine that that's really a hot climate, though. And I'm not going to tell you it's a hot climate, but the example I'm going to show is where the edge of glass performance, thermal performance, was important, not for U factor, but for heat gain control. So, anyone know this? Iconic structure in Seattle, and I don't know if Richard Green is in the audience, so if you have any questions on this project, you can ask Richard Green. It's his baby. He did a great job of the glass engineering on this structure. Olson Kundig was the architect, Front the facade engineers. Arup did the energy analysis. Herzog Glass did an amazing job of glazing that at the top of the tower while people were still visiting. They didn't shut this tower down when they did the renovation. And they used, Richard specified a rigid plastic hybrid stainless steel spacer in there. And I'll show you why in the two areas. There are two areas in the top of the Space Needle. One is the observation deck that I'm showing you here. There's an inside and there's an outside to it. They had a real constraint in the design here. Well, I have many constraints. One was they had to meet the Seattle Energy Code, which is pretty stringent in terms of U.S. glass codes, U.S. building codes. But they also had a landmarks commission that said, you can't change the way this building looks. You can do all the retrofit you like, but it has to still look like it looked like when it was first built. So what you see here is a reverse curtain wall. Now, they basically the mullions are on the outside, not the inside. And it's so that you can get up to the glass and look out without hitting your head on the mullions. But what that did do is it provided a lovely heat sink to the outside, like radiator fins. And what they found was they needed, the only thing between the inside and the outside in terms of thermal transmittance was the edge of glass. There was really hardly anything in the frame to stop the heat flow. And it wasn't so much of a needing to keep the heat in, because they had a chiller system, an existing room for the chiller that was fixed. They couldn't increase the size of the chiller. It was impossible. It was, because of the geometry. And so it was an issue with reducing heat gain in that scenario. And so they needed the warm edge spacer on the glass for heat gain control. And now, if you go down a level, oh, sorry. So this is a quote from Richard. I don't know if Richard's in the audience, you can see he said we needed to get as good a performance out of the glazing system to get the right insulating glass spaces, and that made the difference. And in fact, it was the difference. They weren't going to be able to make it work without that. Now, the thing I really like about this project is the restaurant level just below it. What you see here, large glass, two-sided unsupported glass. And again, the weakest link in that envelope was the edge of the glass. And so what they had to do there was put in the plastic hybrid stainless steel. And there was a choice of lots of different warm edge spaces on the market, of course, that have similar performance. But Richard needed a rigid a warm edge spacer because of the connection system and the support system at the top and the bottom. Because it was unsupported edges, there was a big bite at the top and the bottom, and the way that he worked the structure meant that he had to be able to control the torsion at the top and the bottom. So he needed the rigidity of the plastic hybrid. So by putting the plastic hybrid in the top, in the observation deck, and in this unsupported system, made the difference between them getting the energy performance they needed and also not having to increase the chiller size. And so with that, I'm going to come to my conclusions. For me, it's all about specifying the edge. So if the one thing that you take away from this should be spec the edge and do it wherever you're building a building, whether it happens to be in Florida or in Qatar or in Alaska. It doesn't matter. It's all about controlling the thermal transmission on the edge of the frame and in the frame itself, and also in the edge of glass. If you do that, you have way more flexibility with the choice of the glass you put in the infill. I don't know if anyone went to Olivier Brouillard's talk yesterday from SOM. He had a great parametric analysis, and his conclusion, the data basically showed that if you put a thermally broken frame in that system, you didn't have to have triple pane. You could do it. You could get to the thermal performance you needed with a double pane. And Olivier, you can tell me if I'm wrong there. I see you sitting in the audience there. So basically, a U factor matters in warm climates. It's all about solar absorption in the frame. It's not the delta T air temperature from outside to inside. It's the delta T of the frame temperature from outside and the air temperature or the frame temperature on the inside. So with that, I will stop and ask if there are any questions. Oh, hi, Stanley.
Hi, Helen. Sorry, I missed the first couple of slides.
That's okay. You were otherwise engaged in a presentation.
Something like that. So thank you very much, Helen. Does anybody have a wonderful presentation? Does anybody from the audience have questions for Helen?
Wow.
Yeah, one.
Oh, thank you, Thomas.
Really nice presentation. Just in terms of reducing heat loss in buildings, and in Scandinavia, where I'm from, the energy requirement is now down to 0.45, and the 0.45 watts per meter square Kelvin for the whole envelope. And what we're seeing is that the aluminium profiles and the thermal separators, they start to struggle to meet these. There's simply too much heat loss out through that cavity.
Even though you've got like 3-inch thermal breaks or 75 millimeter thermal breaks.
And you fill the cavity with insulation in the middle,
Yep.
and all that stuff.
Yep.
The question is, what is the response from your industry?
It's a good question. I think they're going to different materials, low lambda materials or lower conductivity materials. That's one thing they're looking at. I don't know whether, probably in Scandinavia too, they're implementing the low E type coatings within the frame. So there are some thermal breaks systems that. So if I think about the thermal transfer through the frame, normally you think of conduction, but there's also convection, because as you just mentioned, you can, if you fill the cavity, if you make the thermal breaks really big, you create some big cavities in there, and so you get a lot of convection. So then you've got to fill those cavities to stop the convection. But then about 15% of the transfer is coming from radiation. So then you can actually start to put some low E coatings, some foils or whatever on those surfaces to reduce the radiation to get the third component down. So those are the things that are happening right now. As for, thinking about alternate materials, I mean, you see these mass timber structures going up in Vancouver. So that's kind of an interesting system. Whether, how that will actually work in larger structures, I don't know. But that's a good question. But unfortunately, in the US, we are not in that situation. We've got to get people to use thermally broken frames everywhere. So I applaud Scandinavia for where they are, but the low-hanging fruit is there. In other parts of the world, we need to start using more thermally broken frames, edge of glass.
Yes, definitely. Still much to be learned from Europe, at least by our North American colleagues.
I would say the technology is there.
Yeah, absolutely. And the example from our first speaker this morning was front and center on that one. Any other questions for Helen? Thank you very much, Helen, for taking the initiative to starting on time.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao!